Manipulating K. Sometimes we have an equilibrium constant for a particular reaction, and the reaction is noted in some table somewhere. And here's an example. SO2, sulfur dioxide, combining with 1/2 of an oxygen molecule to make SO3, sulfur trioxide. Well, perhaps we don't want a 1/2 in our expression, or we want to do some manipulations where this has just all whole numbers everywhere. Well, we can write the reaction with all whole numbers everywhere just by multiplying everything here by 2. So let's write the reaction by multiplying everything by 2. We'll have 2 SO2s, and we'll have 1 O2 now, and that will be in equilibrium with 2 SO3. Now the question is, what is the value of K here? And we know the value of K here, it's some number, we can look that up in a table. But we need to know the value for our new expression here. Well, let's write out what the equilibrium constant expression for both of these reactions is, and then maybe we can find out what we need to do to the value of K to get it for our new equation. So let's write that right over here then. Our equilibrium constant expression right here is products over reactants. All of them are gases, so they all go in the expression. So concentration of SO3. And then we're going to divide it by the concentration of SO2. And then we have concentration of O2 raised to the 1/2 power, which is the same as square rooting it. But I'm going to write it like this. That would be the K for this reaction as it's written. Now let's write the K for the reaction down here, which has been multiplied by 2. So we'll just call that K2. And K2 is, again, products over reactants. And now the SO3 is squared because there's a 2 in front of it. And so is the SO2. Squared O2. Now, let's see if we can find a pattern between these two expressions. So if we look up here, that is to the first power, SO3 is to the first power, SO2 is to the first power, down here to the second power. And here, this is to the 1/2 power, this is to the 1 power. So you'll notice that while we multiplied this equation by 2, we actually end up squaring everything over here. We raise it to the second power. So that's going to multiply all the powers by 2 here. So if we want to relate K1 to K2, we can write this expression down. K1 should be squared, because if I square K1, I will get this, K2. So what that means is, if I take a reaction and I multiply it by some number, some constant all the way across, then it will change the equilibrium constant by raising it to the power that I multiplied this by. If I had multiplied this by 3, then it would be raised to the third power. Now, I could also write an equation going the other direction. Say I started here, but I actually wanted to be there. Well, in this case, I divided by 2, or multiplied by 1/2. So another relationship that we could write here is K2 equals K1, and then we need to take the square root of K2. That is to raise it to the 1/2 power. Same thing, just different notation. So that is how to manipulate K using a constant to multiply it. There's another thing that we may want to do. We may want to change it around so that our products are now our reactants and our reactants are now our products. So let's see what happens when we do that. And I'll use this bottom equation to illustrate that. I'm just going to write it down here. So I'm going to write my products as reactants and my reactants as products. Now, if I write the K for this, we'll call that K -2 because it's backwards. Then we can write the expression, which should be SO2 squared O2 divided by SO3 squared. Now you'll notice that the relationship between these two is the inverse, right? This has been flipped upside down. So if we want to relate this K to that one, we can say this. K2 equals 1 over K -2. So it's the inverse of that. Which should make sense because we always write our products on top and our reactants on the bottom. And if we write the equation in the opposite way, then we'll be switching those positions. And so we just need to do the reciprocal of that. There's one other way that we can manipulate K. And that is we could add two reactions together. And if we add two reactions together, then we will end up multiplying their K's together. Let's show how this works. So I've written a reaction here. This is acetic acid plus water going to the acetate ion and making some hydronium ion, or H3O+. And then I've also written the Kb for acetate, which is the base that this forms when it's in water. So acetate plus water goes to acetic acid again, but now hydroxide. So these are not the same equation. This is the Ka expression, this is the Kb expression, because that's a base and that's an acid. But I just want to illustrate what will happen when we add these two equations together. So I'm going to write out the K expression for this reaction and for that reaction. And then we'll add the two reactions together and we'll write out the K expression for that, and we'll try to relate everything together. So here we go. This is Ka. So concentration of acetate times hydronium ion divided by concentration of acetate, or acetic acid. And again, we don't put in water because that's a solvent and solvents don't go in. Now let's write the K for this reaction. Products over reactants. And since this is a base and it's reacting with water, this is the KB reaction. Acetic acid, hydroxide, all over acetate ion. And again, water doesn't go in. Now, let's see what happens when we were to add these two equations together. Now, I chose these on purpose because certain things are going to cancel out. But if we add this equation to that one, the acetic acid's going to cancel out, and the acetate ions will cancel out, and we'll be left with two waters forming H3O plus and OH minus. So let's write that down here. The net result from adding these up to liquid. And these are aqueous. Thank you. All right. Well, let's write the K expression for this, which also has a special name. It's called KW. The W stands for water because that's water. And it gets its own K because water's pretty important. So this is just this hydronium ion times hydroxide divided by, well, nothing because that's a liquid and it's the solvent, so it doesn't go in the expression. So we have this. Now, let's see what would happen if we took and multiplied our Ka times our Kb. So if we did that, you'll notice that the HAC is on top in the Kb, and it's on the denominator in Ka. And the opposite is true for the acetate ion. It's on top in the Ka expression, it's on the bottom in the Kb expression. So those will cancel out when we would multiply them together. So that would cancel with that, and that would cancel with that. And we should be left with H3O plus times OH minus. And which is the same as KW, which is right down here. So we can actually write another equation that will be important later, which is Ka times Kb equals Kw. But the important thing for now is that when I add equations together, I will multiply their k's together to get the new k. Now that we've gone over all of those operations, we can use that to our advantage when we're presented with a reaction that we don't have the equilibrium constant for. And there's really only a couple of ways of determining an equilibrium constant. One way is to run an experiment and measure the equilibrium constant. And then the other way is to look up all of the reactions that we've already measured and see if we can manipulate those reactions to then produce the reaction that we want to know. And if we can, then we can do a little bit of math. We might need to multiply by some constant value like we did on the previous sheet. We might need to switch the products and reactants around so that way when we add them together it produces the right reaction. Whatever we need to do, and then when we've got that all worked out so that they all add up to be the reaction that we want, we will know whether to square or invert equilibrium constants along the way, and then we can multiply all those equilibrium constants together to get the one that we actually want to know. So that is how to manipulate K.